So this is the introduction to numerical computing with the Perl Data Language, or PDL. I'm Zaki Mughal. I'm on CPAN pause as the Mughal, and on IRC as, I guess you pronounce it Sibois. I don't know. Even though I made it up. So I am close to DC and Baltimore these days. I used to be around Houston. We're not really doing in-person meetups yet, and I would like to do that, but we'll see. Anyway, so I'm a core developer on PDL. I joined the project about maybe 12 years ago. So I know quite a bit about the ecosystem around it. So who here has used any type of tool or language for numerical computing before? So like what? Examples? R. Pandas. Oh, yeah. C. Is Fortran? No, Fortran. And NumPy. MATLAB, yes. Okay. And Octave and Scilab too, which is kind of, I haven't used that one. Okay. But yeah, so PDL is like all of those things, but the Perl version. I guess I missed out APL. How could I? and J and K. But it's like those. And it's been around since, I think, around 1996. It was developed by Carl Glazebrook. I hope I didn't say that name incorrectly. I just know him as Carl on the mailing list. And it was originally created for doing work with astronomy image processing. So they have satellite probes that have sensors, and they bring in images, and a lot of those times those images aren't actually like visible light, and so they might have more than what you would think. Like they wouldn't necessarily be RGB sensor, they could be multispectral images. So you need to have something that can handle that kind of data, which means many dimensions, and that is what PDL is pretty good for. And I got into PDL because I was also doing image processing. I was doing biomedical image analysis. I started out with doing 2D stuff, and then I moved on to 3D stuff. And I didn't necessarily use PDL for doing that research. I used it mostly for prototyping things. But that's just because there weren't bindings for some of the things that I needed, so I would just write it in C++. So, all right. So, what's PDL? PDL is a DSL and library for working with multidimensional numerical data. So what does that mean? So the library has a container data type for homogeneous n-dimensional array. Homogeneous, all the types are the same. It's packed binary data. The usual way you're using it, it's a dense data, meaning not full of zeros. It's you could use it with, of course, with data that's full of zeros, but obviously a lot of operations, when they encounter a zero, they don't really do anything. But if you're working with PDL, the default way, that's what you're usually doing, dense data. And it has a list of dimensions, again, homogeneous, single type, and that container is called an ND array. It used to be called a Piddle, but we changed that name because, well, I mean, it was an international project, so it might have meant different things to different people, but also nobody else in numerical computing knew what that was, so the docs wouldn't correspond to what people already had known about. So that was a better choice, and that's what most people are using as the name for similar types of containers in other tools and languages. And so the DSL part of it, it allows you to create dimension and type aware functions. It includes a DSL called PP, which generates C and XS, It has signatures that contain the dimensions that you're working with and types for those variables. And the dimensions are used to help perform something called broadcasting. Older docs on this used the word threading, but again, that wasn't really the best name because we all use threading for something else. And nobody else knows what that is in this case. So we use broadcasting, which also other languages have now been adopting that terminology. Some history. Originally, this idea was borrowed from this language called Yorick. It was developed at, I think, Lawrence Livermore National Lab, but it was like it only did numerical computing. It wasn't a general purpose language. And both PDL and NumPy were inspired by that in order for them to implement their broadcasting rules. But we're going to get into that in a bit. Okay, so installing PDL, it has several dependencies. I'll talk about them in a sec, but if you can, install it via package manager, because you'll get everything that you need, because some dependencies are optional, and if you want all the functions that are available, then the package manager has them already installed, and the Debian packages are very well maintained. The people who are working on that are very helpful and have actually found quite a bit of bugs on architectures that none of us run. Okay, so the requirement, at the very minimum, you need a C compiler. You need Perl, of course, too, but you need a C compiler because this is XS. Optionally, a Fortran compiler. There are a number of functions that it binds to in the core distribution that require Fortran. For extra functions, if you have libgsl, which is the GNU scientific library, and libproj, which does some transformations, then you can get a couple more functions, a lot more functions actually. So I highly recommend libgsl for that reason. For I/O, it optionally lets you have libgd, which is for reading images. NetPBM also for reading and converting different images. libhdf4, which is a scientific data format, and libcfitsio, which is also a scientific data format. And I've seen that one more used often in astronomy. But HDF4 is very general for lots of different fields. So a tip I would say is set make flags and give it as many processes to run in parallel as possible, because every function is its own file, and it compiles each of those and then links them all together. So it can take quite a bit of time if you're not doing that. So let's get started. So the simplest thing you can do is create a PDL with an ND array. Oh, yes, I can. It is in a browser. Okay, so create a bigger. Oh, okay. Embiggen. How's that? Hopefully the later slides don't get... we can scroll, I think. Yeah, I hope it works. Okay, so the simplest thing you can do is create an ND array with a single thing inside of it, and you can use it just like you're using a Perl scalar for a floating point or an integer. Add it. It uses operator overloading, but you could have done that without PDL. So what's next? Well, it keeps track of the number of dimensions that you have. So you can see down here a number of dimensions. It gives you you can access dimension list as either a Perl list or another ND array. I keep on trying to stop myself from saying Piddle. I've worked on this project for a while, so I'm still not used to it. Okay, so you can get the information. Another way of getting that information is just called info on the thing, and it will tell you it's a double. It's got no dimensions. It's only got a single thing in it, empty. Okay. You can also get the type. That type is an object, and you can get things like how big is that type in memory. There's support for different types, like all the way from byte, short, long double, float double, complex float, complex double. So basically any machine type that your compiler supports, yes.
Why is there an empty list of the?
Oh, I'm doing that so that the output of, I can show you.
That's fine. I think
Yeah, otherwise it'll show the return value. Yeah, and this is live, so.
And the is bytes?
Yes.
Okay.
Yeah. So you could do a prod with that and the shape. Sorry, I'm getting ahead of myself. Anyway, so the whole point of this is to have much more data. So, right, let's make it 2, and you get, similarly, it's a double, but now it says 2, and we can see what's in it. This is how it stringifies. This is how the other one stringifies. And then when you add them, they both add, as you'd expect, like vector addition. All right, but now let's look a little bit more. What else does it do? Okay, so what if we make one of them not the same size? One's 2, one's 3. Okay. Well, when you try to add them, it shouts at you and says the dimensions don't match. It actually throws an exception. It's telling you that size 2 does not match size 3. Okay. What is the thing that it's telling you? It's saying it's at this Piddle PDL ops plus function. And the parameter B is the issue. So we can take a look at it. So PDL comes with a command called PDL doc, which is a way of accessing the contents of the pod for each function. You can do things like search. So if there's all kinds of functions that are available. So like say you could do, so I want to look at the plus thing that they just showed me. So I just type in plus, PDL dot plus, and it gives me the name, the signature, and a big description of what it does. I could have done things like -a plus, and then it would search in throughout the documentation for, okay. That's weird. That's also weird because I just ran this right before. Okay, well, I don't think that's an issue. We'll see. Because I already just ran this and, okay. So let's just look at that signature. So you can give it a -s flag here, and you'll just get the signature. And let's look at what this whole thing means. So the A with empty parentheses means since it doesn't have anything like this, it doesn't have anything like this in front. It's input, and it's got nothing, so it doesn't have any dimensions that it is working, that it needs to work over. And same with B, and then output also doesn't list any dimensions. This O part says it's an output, so this is it's what gets returned, but you can also use it. We're not going to go into this, but it lets you do things in place. So that output could be a piece of memory that you've already allocated, or the thing itself, and then you can do operations like, say, you could do an in-place square root without having to allocate more things, but I'm not going to go into that. That's in the documentation. That's kind of like an optimization type of thing that you would do. So if you have working with very large ND arrays. This all means that the plus function works element-wise because it doesn't require any dimensions to work over actively when it's doing the operation. Okay, and then we can.
What does that swap parameter mean?
Oh, swap. That's extra parameter because it's also used for operator overloading. So when you do operator overloading functions in Perl, there's a swap. So you could have done it the other way around. That helps when we're actually adding a ND array to a Perl scalar or something. So that like if you had the Perl scalar first, and then you had the ND array, then it has to dispatch to the ND array's operator overload list. So yeah. Okay. So yeah, there's a whole bunch of more ops. They're basically all the things that you have as you can overload. Also matrix multiplication. Well, no, that's actually in a different module, but that is available using the X operator. That's the operator that lets you either repeat a string or repeat a list. If we're using it here to do matrix multiplication because it's available.
Just to clarify on that, the swap, that's saying that you can express the operation either as the scalar and the matrix, or the matrix and the scalar, and in both cases.
Yes.
Is that correct?
Yes. Well,
Normally, the operator would apply to the first parameter, and that says, oh, if it's the second one, then use this code.
So the question was, the swap was about the scalar. Okay. Yeah.
The order of
Yes, the order, because all an infix expression is just a different fancy way of doing a prefix with a function called like think Lisp like, right? Anyway, yeah, so there's a whole bunch of these, and most of them are also element-wise. So there's plus, mult, whatever you expect, divide, greater than, less than or equal to, what you expect, basically.
The string plus
It's being used here for something else, but yeah. There's also other stuff for being. Sorry. Yeah. That name was for using. It has to be. This is the name of the function, not the name of the operator. Yeah. Yeah. Okay. All right. So I don't know if this will scroll. I might have to jump out. But let's see. Okay, I might have to jump out just to scroll down, but that's not an issue. So, okay, so what if we actually tried to get those dimensions to match? What if we put all of those individual elements inside another list so that the size of it would be 1 by 2? Or no, sorry, size of 2 by 3. Let me jump out. So you see the size of P is just 2. The size of Q is 1, 3. That's the dimension list. And then you can access a specific element by using the add function. I'm just throwing that in there. It returns a Perl scalar. I'm not going to talk about this, but that also means that it can work with bad values. I'll have a link at the end about that, but we're not going to talk about that here. But when you add them this time, instead of throwing an exception, it adds these and gives you basically the 2 and the 3 as the actual dimensions of the output. So basically it added 1 and 2 to each of these. 1 and 2 gets added to 3, you get 4 and 5 added to, so 4 and 5, 5, 6, and 6 and 7. There's another way you can do that. You can just use the 3, 4, 5 in a single one-dimensional thing, and then you can transpose it. Then you'll also get the same thing, a 1 by 3, when you transpose it. You get the same output. Oof. Okay. Yeah. I'll just do it this way. Okay. So there's another way you can do it. So PDL has this idea, something called dummy dimensions. You can insert a dimension that just is going to be one of size 1 by default right in front of everything. So by default, if you just give it a single number, it'll just use that as a position and give you a dummy dimension of size 1. Those dummy dimensions are used to match up with other dimensions when you're so remember when I had the error about those dimensions not matching up, these broadcast dimensions not matching up? If you insert a dummy dimension of 1, that matches with everything because it's 1. So that's what that's used for. And with that, you get exactly the same thing as before. You can get a 1 by 3 that way. So there's multiple ways of doing this. It's Tim Toady, right? And interestingly enough, there is no limit other than your memory of how many dimensions you can add. So I can add 1,024 extra dummy dimensions, and this is what it will look like when it's stringified. Well, okay. If you got all the new lines, it would be a bunch of brackets all around. That's an interesting feature because all it does is it adds it to the list. It doesn't allocate any more memory or anything. It just changes how it loops over things. So it's the same memory as before. The same numbers in the same memory address. So interesting enough, there aren't that many other tools that do that. A lot of them have limits. Like the old Fortran had a limit of 7 dimensions. Newer Fortran has 15. NumPy used to have 25, then it became 31, that type of thing. They have a hard-coded limit to how many dimensions that you can work with. Although, if you have that many dimensions, you probably have other problems, and that's your data. Sorry. But PDL lets you do as many as you want, so you're not restricted. Okay, so what I'm going to do here is I want to do a modulus on the contents of that result we saw here. So I wanted to find where is it even. Wait, can you see? Can everybody see? Is it 2? One more? How's that? In the back? You're good? Okay, good. Sorry. If I do a modulus on the contents of R, it'll give me a modulus 2. It'll give me a I'm doing modulus 2 equals 0, so it'll give me wherever everything's even. There's no remainder. And so you get basically this output. This is basically like a logical mask. Wow. Okay. So what you can do with that type of thing is you can use these other functions called any and all, and basically check if there's anything that's true inside of that ND array, then just it'll turn true, and all does the same thing, except all of them have to be true. So you can see that any is 1 because there are true values there. All is 0. And if you try to, those functions are mostly used for when you're doing some things like conditionally, you want to check something. Because if you got rid of this any, it'll throw an exception because you probably aren't doing something correctly. Because this is it's an object. It's going to be true. It's not undef or a falsy thing. So you don't want to accidentally stringify or something. But so in a Boolean context, if you're not using something that turns it into this type of thing, then it will throw an exception. And then what I'm doing here is which, and that gives you the indices in memory that corresponds to the places where it's true. So what do I mean by indices in memory? Well, if I use this function called sequence, what it does is you give it a number. Oh, in this case, I'm not giving it a number. I'm giving it another ND array. It's going to make a sequence of the same size as the input ND array. And what it does is goes from 0 till the end and tries to fill them in increasing order. And so that's what these indices refer to, is the corresponding numbers that this sequence is going along, because this is actually, those numbers are actually where they are stored sequentially in memory as well. So that's how they're packed. So if you did a flat, which gets rid of the dimensions and stores them as with one dimension, you can see them like that's how they are. So that all that does is it removes the dimensions. It actually doesn't even change the. It doesn't allocate something new. It's just a different view on the same memory. So what can you do with that mask that we just made? So you can use where. What where does is you take the mask and it looks up wherever that thing is true and gives you a view onto those locations. So what can you do with that view? Well, you can assign to it. So this is a way of assigning to this view, this is still connected back to the original ND array. So we can see when you assign to it, it assigns all those places to 42. In fact, this could have been stored somewhere instead. It could have been like my slice equals that, and then slice, you assign to the slice, and it would have still worked. It's not just that it's an L value. That's how it works as an L value. You know what an L value is in Perl, right? It's on the left side of an assignment. And okay, so what if you did where and you did something that it couldn't be? Like modulus cannot be above the thing that it can't be above like modulus 2 cannot be outside the range of 0 or 1. If you tried to look for where it was 3, there'd be none, and then you do a where on that, it'll be empty. So you get an empty, that signifies that there's nothing there that you can do. So yeah. So there are other ways of creating commonly used ND arrays. I really want to say Piddle. Sorry. Just like if anybody's used, say, MATLAB, it's got zeros, which gives you an ND array of just full of zeros of that size that you give it. There's ones, which does the same thing and gives you full of ones, the very two important numbers. Sequence, which we've already seen. It goes from 0 up till the thing is filled. Xvals, which along the first dimension, or zeroth position in the dimension list, it goes in increasing numbers until it gets to the end of that dimension. Y-vals, which does it for the one position in one in the dimension list. You can see it's going the other way. And then you can do z-vals, and this is why I made it a 3x3, is so you could see z-vals. Z-vals does that in that position along that dimension. And there's r-vals, which does basically, distance from the center. So center is 0, and then, this is like square root of 2. Is it 2 square root? Yeah, so, those look familiar. Like Pythagorean. And then the random, which is the random, uses a random number generator to do that. So important things for statistical work. So what I'm going to do is I'm going to show what you can do with some other things that are available. So I'm going to start out by a 9x9 zero, an ND array full of zeros. And I'm just using that to indicate a size. And I will use this function called xlinvals. And what that does is it uses the size of the thing you're giving as input and then fills it from on the real numbers or from the start to the end. So when you run it, 0 to 1 for 9 values in the x direction, and then this one, which is that from negative 0.5 to 0.5 in the y direction, just like y vals and x vals. And what that is useful for is when you combine them together and you can do like a calculation, like a gridded calculation, you can combine them and, compute at each point using those inputs. That's what that's made for. There's identity, which you'd expect to have in a language for doing things with matrices, which is the identity matrix. There's stretcher, which is the name that PDL used for doing a diagonal. So control. So whatever is in this one-dimensional thing becomes the diagonal of the two-dimensional ND array. Okay, so that's like the basics of, getting some data, working with it, but that's all just numbers inside your program. What if you want to get stuff from outside? Well, there's different I/O stuff, and what I'm going to just use is a thing for reading images. I have a module that has a bunch of test images that are common in image processing, and I use this function, rim, which is read image, which will read in and convert it into an ND array. And then you can see that what you get out of that is you get a 512, 512, and 3 dimensions. And what that represents is 512 width, 512 height, and 3 for the channels of RGB. So has them split, and these are bytes. The type is a byte, not a double, like all the things we were looking at earlier. Double is the default, that if you don't specify a type, then double is the default. So we can work with bytes here, and this is just the documentation for the rim function. Same thing with, you use PDL doc, and you can read it in just the documentation for that function. It's quite a bit of stuff. And this is what it looks like. I'm going to use, so there's several ways that you can plot things in PDL. There's like 3 different back renderings engines. There's one, pgplot, which is like the original one that PDL was created with. And it's really old. A lot of the astronomy community loves it. There's even like a new implementation of the same API by somebody else called Giza, because it's based on Cairo, I believe. the chirographics library. But the Fortran code still exists. It's not being really updated anymore. There's some licensing things we're working out with, I think, Berkeley, where it's hosted. But yeah, pgplot exists. I don't use it, but a lot of the people who made PDL do. There's plplot, which is a C library with many, many bindings to many languages. There's GNUplot, which I'm using here. It's not a library. It's actually a program, and it's a scripting thing for just plotting stuff, and it has many front ends, meaning it can render to like PNG, SVG, X11 windows, a Windows window, Aqua on Mac. So it has both a graphical interface, a WX, also has a WX output, and it has other things like PDF, lots of different things. You can even use it in a terminal using the Tektronix output, the Xterm supports. But I'm using it here because I have support for it inside of this thing, which is, I haven't really mentioned it, but this is a Jupyter Notebook with a Perl kernel. So I have support for it through a plugin. Whenever you put this GP at the end, it will try to replot the thing. And right now it's plotting it as a SVG, and it puts it underneath. So what I'm doing here is I use the GNUplot thing, and I use the image method on that GNUplot window, pass it the ND array, and I just say make it square, because if you get rid of making it square, then it'll draw it at whatever aspect ratio it wants, and that looks weird. So make it square, because it's a 512 by 512. Okay, so what you can do with that thing is that there's and the reason I'm doing the image processing is because it's best to do large things. You should, as an image, or just visualizing things as fast as possible, it is like a number one principle in when you're working with data, is, get a big overview of things. So what I want to do is I want to slice of the indices from 0 to 255 and 0 to 255 in the 0th and the first dimension, and plot it. So basically that's going to do the bottom left corner. As you can see, like this was where it starts at 0 in the bottom left here. That's just how it was read in. That's why it's doing that. And that's how this image thing handles that thing. So like in some places the coordinate system is flipped so that 0 might be in the top, but it's in the bottom here. So anyway, we can also do slices. There's another way of doing slices with negative indices. So that's how I'm doing that with to get the other from the other direction, the top left. Same in the X, but get the top left by doing negative 256 to negative 1. Negative 1 being the last in that dimension. And plot it, you can see it's the top left. Now, what I want to do here is I want to split into, what I want to do is I want to visualize the image, but they're separate channels. Because if you just extracted out that channel, and by the way, up here when I was doing the slice, notice I didn't have to indicate that like which ones I wanted of the channels. I only used the first two. The rest got, if you for the first dimensions, whatever you're doing, you can just you have to, if you're gonna slice those, you have to specify what they're gonna do. What you can do is you can also do colon here, and that will keep all of the things in that dimension. It's very similar to the way the MATLAB has that syntax. So you keep it'll have all of the contents of those dimensions if you use a colon. Keeps them as they are. but I can leave it off because it's after the ones that I'm interested in. So here, what I want to do is I want to create several of these RGB cubes, but have them only contain the contents of that channel, the R channel, the green channel, the blue channel. So what I can do is I can use an identity matrix, and then what I do is this slice, if I put a star there, that inserts a dummy dimension for that location of size 1 by default, and another dummy dimension. So 2 dummy dimensions of size 1. And these are placed in the front. And I don't have to specify any of the other ones. They're kept as they are. So it will be, so what this will create is a 1 by 1 by 3 by 3 ND array. And then if I multiply that with Mandrill, it will match up those dummy dimensions with the first dimensions of Mandrill, which are the width and height. And then the rest of the identity matrix is applied to the remaining in the RGB cube part. And so what that does is it actually, when I do this, this is basically trying to see how this is the sum of the first one of the things that comes as the output. Sorry, this last dimension. Okay, so you'll get a different output this time. You'll get X, Y, RGB, and then you'll get 3 here of the different things that we've split out. And if you do this sum over thing, what I'm trying to do is find the pixel count of each of these last, and the things in the last thing. That's what sum over does. It reduces the, well, what clump does in the first place is it smashes these two, 0 and 1 together, and you get a really long 512 times 512 dimension, and then 3 and 3. And what a sum over do it'll go over the last dimension, and it'll reduce it and sum everything along that. And then so we can, this is to verify that it only contains red pixels, green pixels, and blue pixels. Sorry if this is a little bit mind-bending. Dimension doing, yes.
Is that a spurious open paren, closed paren in 29?
No, that's just to make sure that it doesn't use return the output of say.
Oh.
It suppresses it in this environment. I could have put undef or something too. Yep. So now I can just plot those. Also with GNU plot, I'm going to use a multiplot thing. And what this slice does, this thing, comma, 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 it's if I left out this, I left out the colons. That's another way of just keeping them as they are. And then what I want to do is I want to take the 0 slice of that dimension, and what it does is it does a squeeze operation. A squeeze operation is it takes dimensions that are of size 1. It does the opposite of dummy. It removes dimensions of size 1. So this will make it so that I only get that 0th RGB cube, the first RGB cube and the second RGB cube. And then that dimension goes away because it's only selecting that. And so you have 3 RGB cubes. I plot them one after each other, and in a multiplot, so they get plotted side by side. That's what you get. There's another way of doing that. You can, instead of doing this selecting and slicing stuff, you can use dog. And what dog does is it takes the last dimension and gives you that many number of ND arrays. So a list of them. And so what I'm doing is I'm looping over the list from dog. Why is it called dog? Because it's the opposite of cat. There is a cat function too. I don't know if MATLAB has cat for sure. I don't know if it has dog. Anyway, so same thing. To do a different way to do the same thing. Now what I wanted to do is, okay, these are all in separate plots. What if I wanted to actually put them all together in one plot? What I can do is I can move dimensions around. So what this does is it moves the last dimension to be the first dimension. And you can see that that's what it did. 3 ends up becoming 5, right after the first 512. And then what I can do is I can either reshape it by explicitly saying like what I want the new dimensions to be, 512 times 3, okay? So that the x's will become like all next to each other. Or I can use clump, and it'll clump the first 2. Okay, and then I plot that and get that. There's another way of, and what if I want to do it vertically? Well, I can move the first dimension to there and clump it, and I'll get a vertical. And I mean, if you change this to -1, 1, instead you'll get interlaced stuff, and you'll get a really long mandrel with RGB, RGB, RGB lines all the way down. Okay, so let's do some more image processing. This is how you can do a histogram. What I'm going to do is I'm going to do a histogram of just the RGB channel. I give it a range because it's 0 to 255, it's bytes. I want to split it into 16 things. And this is going to be the bin centers of the histogram. This is the number of counts in each of that bin. I plot that with GNU plot. And you can see this is the contents of that, bin centers and the counts. I used cat here so you can see them side by side. And that's the histogram. And I'm thinking, based off both looking at this and this, I think I could put a threshold right here. What I wanted to do is just keep the highest number of places where it's red. So I put a threshold there. There's a way to get this line here and mark it in GNU plot. And what I can do is I can use that where from before. And so I use the slice, see if it's less than or equal to that threshold, and then assign any place where that is to 0, and then it goes away. And then what I'm going to do is I'm going to glue 2 things, or glue 3 things with each other along the 0th dimension so that they can be side by side horizontally. And I glue the original mandrel with it with a bunch of zeros of length 10 and the threshold one. And so what happens is that 10 gets extended all the way down because it broadcasted when it was doing that. And then this is the original, and this is just the thresholded version. Usually you'd use a binary image if you're going to do, or a grayscale image if you're going to do these type of thresholding, but I wanted to, combine several things together so you can see that what it does. So there's you can access a bunch of different special functions, and this is why I said you should have the GSL. But I don't know if we have enough time. I'll just I don't know. I can scroll by stuff and quickly describe it. So this is just a plot of the cumulative distribution function of a Gaussian, different ones with different values for the standard deviation plotted together. And notice that I used a bunch of broadcasting things to do it so that I only used one line to get the output. So if you switch dimensions around, every function, even the ones in GSL, get broadcasting, even though it's just calling a function that only takes one input. It doesn't take a vector type for GSL. It gets broadcasted because of the way PDL works. It's a DSL that will do the looping for you. And it will do it all in C and then give it back to you in Perl with a wrapper. So it doesn't, cross the boundary when it's doing that. So that's how and then the plotting here, because of how the GNU plot binding that we've done is written, it also does threading, and it can plot multiple plots at the same time using that output. There's other things in GSL for doing integration. This is just comparing doing the CDF, the way that it's a predefined function for the CDF versus using a callback, which is the PDF, the probability distribution for a Gaussian, and then just doing integration on there from -infinity up to that point. And then you can compare. I just put a gap between them so you can see. There's some difference somewhere. You can see a little difference in the curve, and I did a min and max to see where minimum 0 difference, maximum 3 to the -16th difference between these two curves. There's PDL stats. It has a number of things for doing things like k-means, certain types of linear regression fits. And in this case, I wanted to show how you could do it with PCA with that. PCA, do I need to explain PCA? Well, the simplest way to do it is it takes your data and transforms it in a way so that it creates, you have data and it has features, and it transforms it in a way so that it's aligned, and it creates new features that are a linear combination of those original features, such that each feature gives as much explanation. That linear combination of features gives as much explanation of the variance in that data along that direction. So it's kind of like if you have a data point and you created ellipsoids around it, and each of the axes of the ellipsoids was in the maximum thing to close around that data. So this is just going to make PCA on it. This is like pandas. This is data frame, which is actually using PDL underneath. And I use PCA from PDL stats GLM. It gives you things like eigenvalues, eigenvectors, and the percent variance explained. And I plot that as a blocks plot. So the first principal component explains this much, second much, and second does that much. And then what I can do is I can compare a plot of the principal component one, or the 0th one with the first one, and this is a plot of the different types of irises plotted in a. If you plotted it originally, these things would be aligned a different way, but if you plot them along the principal components, it like axis aligns that ellipsoid that I was talking about. So it lets you better understand that these things are separate from each other, not putting those points together. This is just an example I'm not going to talk about. And this is finally a demo of OpenCV, which just came out earlier this year, OpenCV binding for PDL. And yay, it's my close-up. Anyway, so this is just a hard detector, which is it's been trained to capture face things. And then there's a line segment thing. I don't know if you can see it. But this is OpenCV running from PDL. And I have some resources. I'm going to put this online. But are there any questions? Yes, Brett.
Do you have a link to how you can get this working in Jupyter Notebook, or how to get that set up? Because I think that's awesome.
Slides or just Jupyter Notebook itself?
No, the PDL in the Jupyter Notebook.
Well, it's just, okay, so you can, if you install devel iPerl, it'll give you this kernel, and then you can, sorry. This is devel iPerl. If you just install that, and you install Jupyter Notebook, and if you run, right now, if you just run iPerl -- version, it'll install the kernel, and it'll register it into Jupyter Notebook. I think I have it all in the README for it, but it can run any Perl code. It's not just PDL specific. It's just, this is very nice. Otherwise, I would have made like a LaTeX thing, and it would take forever to get all these images into it. So,
That's huge.
any other questions? Yes.
Is there an text that you can read to find out all about how to use it?
There is a PDL book. It hasn't been updated in a while, so it uses the old terminology. I'm planning on adding more examples to it, filling it up a little bit more, but it is a good place to start. There's this, and that's good for an intro. There's an advanced text as well that's on archive.org. It's called Practical Magic with C and PDL. I will add it as a link as well here. And that lets you, how do you add new things that broadcast and wrap around either C or Fortran, or right now it doesn't have any information about C++, but OpenCV is C++. So this required some changes to the code to make it compatible, but that's why it came out this year. So anything else? Any other questions? Yes.
How does it compare with NumPy?
NumPy has a large community. NumPy doesn't do all the broadcasting thing. That's the main thing that I think you should take away from this, is that PDL uses broadcasting everywhere, so you don't have to write any C code. If you don't use in place and some other techniques that are more advanced here, that puts pressure on the RAM, on your memory, if you have very large ones. And sometimes you change, because the way you can change dimensions, that doesn't change how the thing's laid out in memory. So things like spatial locality for the speed of how you loop are important, but that only becomes an issue if you have very large data sets and you're doing many complicated operations on it. So R has a very similar design, except it doesn't have as high dimensions. I have a binding for R from that gives you back PDLs. I need to update it because both of those things have changed. So look for that later this year. It's called Statistics Nice R. But yes, well, any other questions? No more questions. All right. Thank you very much.